A very warm welcome to this IEAGHG webinar on the Global Assessment of Direct Air Capture and Storage Cost, Scale and Potential. My name is Jasmin Kemper. I'm a Senior Technology Analyst at IEAGHG, and I will be your moderator for today's webinar. So who is IEAGHG? For those of you who don't know us, we are a so-called technology collaboration program under the IEA's Energy Technology Network. And we are organized under the IEA, but we are functionally and legally autonomous. So all views, findings, and results in our publications do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. So we are part of the IEA Energy Technology Network since 1991. We are comprised of about 35 members who set our strategic direction and technical program. We are also technology-based organizations, and we try to inform policy but not define or to lobby policy. So our core activities are the assessment of climate change mitigation options with a focus on CCUS, and there we track capture and technology and development costs. We also track the progress in geological storage performance and monitoring. And also we try to provide our members and the policy audience with the independent technical input that results from our studies. Some of our flagship activities include our technical reports. We have published so far more than 350 studies on a multitude of aspects related to CCUS. We also run a number of international CCS research networks, including on costs, risk assessment, monitoring, modeling, environmental research, and on high temperature solid looping technologies. We also organize some flagship conferences, first and foremost the GHGT conference series, but also the post-combustion capture conference. We are also organizing an international CCS summer school, which now has more than 560 alumni from more than 59 countries. And the next summer school is planned to be in Indonesia in summer 2022. We also do peer reviewing activities for other organizations such as IEA, the US Department of Energy, the US EPA, and CO2 CRC. We are also involved in international regulatory developments. So we are active in the UNFCCC, the IPCC, the London Convention, and in the ISO. And we also collaborate with a lot of similar organizations like the Carbon Sequestration Leadership Forum, the Carbon Capture and Storage Associations, the Zero Emissions Platform, GCCSI, and many others. And here a bit advertising. I mentioned the GHGT conference. The next one will take place in person in October in beautiful Lyon in France. And it's the leading conference for CCUS for more than 30 years now. And this one will be hosted by Club CO2. And you can expect over 500 presentations in 71 sessions in 7 parallel streams, in addition with panel sessions, keynotes, and social events. And we have already received over 800 abstracts. And if you want further information, then please go to our GHGT website. At this point, also a big shout out and thank you to our members, which you can also see here. We have member countries and we also have industrial sponsors, and they make our work possible, and they also steer our technical program content. So with this, I would like to hand over shortly now to our presenter for today, Yourkcan Erbay. Yuri is currently a consultant at Emerald Energy, where he works on a range of topics on greenhouse gas removal and carbon capture, utilization and storage technologies, with a specific focus on power generation applications, direct air capture, and bioenergy with CCS. He delivers projects for international public and private clients, focusing on all aspects of technology development. Before joining Element Energy, Yuri completed his master's degree in sustainable energy futures at Imperial College London. His thesis project investigated the technical feasibility, viability, and public desirability of GGR business models from a design thinking perspective. And as mentioned, the results of today were published in an IEAGHG report in December 2021. And if you want to access this report, please contact my colleague Tom Bilcliffe, because IEAGHG reports usually have a 6-month embargo. But if you are a member of one of our sponsoring organizations, or if you live in one of our member countries, you can immediately access the report before the 6-month holding period is over. The presentations and recordings of today's webinar will be made available. And if you have any questions, then please put them in the question box for this webinar. You'll find that on the right side in your panel. There is usually a chat and a questions function. Please use the questions box instead of the chat. Now I'm going to give over to Yuri.
Can you see my screen?
Yes, we can see your screen.
Perfect. Thank you very much, Jasmin, for that great introduction, and a warm welcome to everybody from me as well. Thanks for joining this webinar. First, a quick note about Element Energy. Element Energy is a UK-based net zero energy consultancy working across many of the main energy sectors, including CCUS, greenhouse gas removals, and industrial decarbonization. And we work across the public and private sector. This study for IEAGHG was conducted the first half of 2021. So especially on the policy fronts, some important developments have happened since then. The slides are not updated to reflect the report accurately. But a brief context around the study is that direct air capture with CCS, or DACCS for short, is identified as a key decarbonization solution by many governments and models and decarbonization pathways. However, the current understanding around costs and future projection of costs are immature and highly uncertain. So this study aims to fill in that gap. And the study revolved around 4 main sections or tasks, so to say, including, first of all, developing a high-level techno-economic model to understand the current costs and tests sensitivities around important parameters. And secondly, we evaluated, using this model, key global siting factors, both quantitatively and qualitatively. And these factors included energy prices and emissions, CO2 storage and transport availability, land and water requirements, CO2 utilization, flexible DACCS operation, and policy and regulatory DACCS space. Then we reviewed the DACCS representation in integrated assessment models, or IEMs, and developed some best approaches for integrating DACCS into future models. And lastly, we provide an overview of the current policy space and list some potential recommendations, policy and regulatory recommendations to accelerate uptake of DACCS. In today's presentation, I will talk the most about point 1 and partially points 2 and 4. But for all the other bits that I won't have enough time to touch upon, I encourage everybody to check out the full report, as Jasmin mentioned. It should be available to the general public in about 3 to 4 months' time, if you're not in one of the IEAGHG member countries or organizations. So first, I would like to start with a bit of background on DACCS. Unfortunately, current deployment rates of DACCS have been very low at around 11 kilotons of CO2 removal per year. And the larger DACCS plants to date is Climeworks' Orca plants in Iceland, which was commissioned last year with a capacity of 4 kilotons removal per year. However, there are plans for deploying larger scale projects. We estimate technological readiness levels, or TRLs, of DACCS to be around 4 to 6, with 6 representing more established technologies and companies, and 4 representing more innovative approaches emerging out of the R&D stages. But as in any technology, of course, some applications are likely at much lower TRLs as well. On the other hand, other parts of the DACCS supply chain, such as the CO2 transport and storage, are well-established technologies and are at much higher TRLs. This study focuses on two prominent DACC technologies, which we name liquid absorbance and solid adsorbance. Liquids, and here represented by Carbon Engineering's process diagram, use hydroxide solvents to capture CO2, and the CO2 release process currently requires reaching very high temperatures around 900 degrees. Now, reaching that high temperatures requires using natural gas, and currently CO2 from that combustion is co-captured in the process. However, since natural gas is used, this process may have some upstream methane emissions. The air capture component of this system is modular. However, since very high temperatures are acquired, efficiencies improve greatly with economies of scale. So liquid technologies tend to perform much better at larger scales. On the other hand, solid adsorbents can be slightly more modular. Here, the schematic is from Climeworks' system, where the single container can operate both in the adsorption and desorption mode, and it requires temperatures only around 80 to 120 degrees. Therefore, waste heat sources such as nuclear waste heat from the industry, or geothermal heat, or heat pumps can be used as a heat source. And since a single container is required, it's much more modular. However, since physical CO2 is handled, still the process benefits from a level of economies of scale. And next, I would like to introduce you or talk a bit about our methodology and the techno-economic modeling. You can see here some of the inputs and the outputs of the model. And inputs included various cost components such as CapEx, cost of capital or cost of finance, operational costs, which we separated from energy, demand, and price, which were some of the most important parameters, and then downstream costs such as transport and storage. And our outputs included emissions from various sources such as fuels, chemicals, upstream methane leakage, construction emissions. However, these were based on literature values, and we didn't complete a dedicated life cycle analysis. And some emissions, such as emissions from transport and storage of the CO2, are missing. We calculate DACC costs in something we call levelized cost of DACC, or LCOED for short. This is similar to levelized cost of electricity. So it's basically the total costs the plant incurs over its lifetime, discounted, divided by total CO2 captured. We first calculate this on a gross basis per ton of CO2 physically captured from air, and then we use the emissions to determine net costs per ton of net CO2 removed. Our main data sources were literature, publicly available information from technology developers, and some amount of confidential information by tech developers. And as I said, we consider both solids and liquids separately, but there were several other sensitivities or scenarios we considered. One of them was hybrid plants, which use both electricity and heat, and electric-only plants. And another factor we looked at was the scale of plants. So for our baseline assumptions, we used a 1 megaton per year capacity plant, but we also considered a smaller 100 kiloton per year plant. And lastly, we looked at first of a kind costs separately for plants which would commission in mid-2020s, and end of a kind costs, or NOAC costs, for plants which would commission in 2050, but the 2050 was a representative year, and NOAC represents approximately 5 to 7 doublings of an initial large-scale DACC capacity. And depending on how fast DACCS is deployed, it can be reached earlier, around 2035 or 2040s. Now on to some of our results, and on these slides, the graphs on the left represent liquid technologies, the graphs on the right represent solid technologies. So here emissions are shown in kilograms of CO2 per ton of CO2 captured. So a value of 100 represents 10% of captured carbon to be emitted throughout the process. And some of our assumptions were that we assumed solar PV is used as an electricity source with the associated embedded carbon. And for heat, we assume liquids use natural gas with co-capture, and solids use nuclear waste heat with modest amounts of associated emissions. So we can see that for liquids, the hybrid FOAK plants have relatively high emissions, around 16.5%. And this is mostly due to upstream methane leakage, which is the gray bar. But this reduces significantly for the NOAK plants as natural gas supply chains are decarbonized. And for NOAK plants, overall emissions factors are around 6 to 7%, which aren't that much. For solids, NOAK emissions are found to be much lower, around 3 to 4%, but the electric FOAK plant may have higher than 10% emissions because still solar, because of high energy electricity demand and still the embedded emissions in the solar PV. But overall, these emissions are much lower than what we see for some other negative emissions technologies. So they're not likely to be very inhibitive if low carbon energy is accessible. Next up are FOAK costs, first of a kind costs. And here the bars represent the LCOED in terms of dollars per ton of gross carbon captured, and the red diamonds show overall costs on a net basis once emissions are taken into account. That's why they're higher. We assume that, so one assumption I want to highlight is that we assumed solar PV costed $68 per megawatt hour, and this may come off as relatively expensive for some of you, but the reason we did that was solar is an intermittent source of energy, so it won't be able to supply a baseload DACCS plant unless battery storage is used or some sort of other grid balancing mechanism is used, maybe power purchase agreements are used. So the cost is likely to be higher than the pure cost of producing the electricity. That's why we went with a less optimistic and more modest assumption here. However, we still considered the option of low cost electricity, and that's what the bars on the far right on each graph indicate. They show a low electricity price situation where solar PV was $24 instead of $68. In general, there are some key trends here. For 1 megaton plants, liquid solvents came out to be cheaper than solid adsorbents. However, liquids scaled much less favorably at smaller scales. So you can see that the difference between a 1 megaton and 100 kiloton plants are substantial because liquids really benefit from economies of scale. Whereas for solids, the difference between different sizes were minimal, showing their modular nature. Also for solids, the biggest cost component was non-fuel OPEX, and that was because of the adsorbent prices. Currently, novel chemicals are used as adsorbents, and they are very expensive, but once economies of scale are realized in the future, there may be significant room for cost reduction in that department. Moving on to N-of-a-kind or NOAK costs. By the way, on the previous graph, we didn't have electric-only liquid plants because currently they don't exist. They're in the R&D stages, and they're expected to be available for the NOAK stage. And this time, our baseline solar energy assumption reduces to $50 per megawatt hour. But the graphs and the trends are mainly similar. For 1 megaton plants, liquids are found to be slightly more cheaper than solid DACCS and have a similar relationship between larger and smaller plants. Liquids scale much less favorably, and solids scale similarly between the small and the larger scales. So for liquids, the lowest costs achievable are around the $200 mark with the baseline energy assumption, but in the lower electricity price case, the lowest costs we see are around $150. For solids, even the low-cost electricity case only reaches around $200. But we included one more case here, which is the far right bar, and shows a special situation where adsorbent prices are reduced even further, because there's quite a lot of room for improvement here, and how much those costs can reduce are slightly uncertain. And you can see that solids may start getting more cost competitive if this is achievable. And in general, all of these costs are higher than the $100 per ton industry target, which is quoted a lot by technology developers. But as we will discuss in a bit, in certain circumstances, these costs may be significantly reduced. And finally, I want to talk a little bit about sensitivity around these costs. So these tornado graphs show how LCOEDs change when certain parameters are changed plus or minus 50%. For both technologies, CapEx and plant lifetime are very important parameters, especially reducing the plant lifetime to less than 20 years it would be very detrimental for overall costs. For liquids, electricity price is an important factor because of its higher electricity demand. And for solid DACCS, as we discussed, adsorbent prices are very, very influential. Next, I would like to talk a little bit about the global siting considerations in these specific circumstances we explored, starting with transport and storage costs. In general, we found that for standalone plants, TNS costs were around 10 to 15% of overall costs. And here the first 4 bars show transport and storage costs for a standalone plant for different assumptions around storage and transport. In general, costs are around $20 to $27. Don't show too much variation except for an onshore project, which can have some cost cutting, and this may be achievable in countries like the US or Australia, for example, probably not very suitable for Japan or Europe. And a base case would be a plant situated in a cluster, industrial cluster, using shared infrastructure, and costs can be very low in this kind of a situation. And finally, the worst case you can see is for a smaller plant transporting over long distances, and costs, TNS costs themselves are prohibitively high in such a circumstance. Perhaps the most important parameter affecting DACCS costs is access to energy and energy prices. So this graph is showing how overall LCOED for a 1 megaton solid DACCS plant changes at the NOACS stage, changes according to electricity costs, which is on the x-axis. Different colors represent different sources of electricity, and circles are hybrid plants using both heat and electricity, and squares are the electric-only plants. And there's a linear relationship. As electricity costs reduce, overall costs directly reduce, and squares, the electric-only plants are as expected, show greater sensitivity to electricity prices. So regions with more expensive electricity would be more suitable for hybrid plants. And in this instance, costs can reduce to around $200 if cheapest forms of energy are used. We also consider different heating sources, here represented by the red dots, and you can see that if low carbon heating is used, whether it is nuclear heat, geothermal, or free waste heat, then costs can be manageable, or costs are much lower than using unabated gas, and even a low gas price assumption still skyrockets the cost because of all the emissions in the process. The graph would look very similar for a liquid plant, and that's why we didn't replicate it here. Essentially the same linear relationship, but the curves are a bit more steeper because the electricity demand of a liquid plant is slightly higher. But overall, it's very important to have access to low carbon, low cost energy. And some of the lowest costs shown here, around $10 to $20, may be achievable as a pure solar production price, for instance, but once you factor in battery storage or grid balancing prices, they may be more difficult to realize. And also, finally, liquids would reach around $150 at the lowest cost end. Next, a quick look at flexible DACCS operations, which is floated around as a possibility to use perhaps curtailed electricity at a lower price. So this idea that the DAC can follow renewable energy generation. And here we provide a quick what-if estimate, back of the envelope calculation. So case A is representing a base case of a large 1 megaton liquid NOAC plant at $206. Case B looks at that plant, but the load factor is now 30% rather than 90%. So the capex and financing costs are tripled. And case C looks at that situation with lower cost electricity, so only $15 per megawatt hour rather than 50. And you can see that costs are still higher than the baseline. And in case D, where electricity is free at $0, then costs are better than the baseline, which may be very, very hard to achieve at 30% load factor. And finally, case E is looking at 15% load factor, and then the capex costs are essentially too high to justify this kind of an environment. So from our analysis, it appears like flexible DACCS operations may not be the most optimum solution. Finally, a bit about the land and water requirements. Won't go into detail too much, but this image created by Clientworks nicely summarizes how much area is needed for various GGR technologies to remove 8 gigatons per year, and DACCS requires much less area than some of the other options, especially the biomass-related technologies. Even when solar PV is taken into account. And depending on the energy source, if nuclear is used or offshore wind or gas CCS plants are used, then the area required is likely to be much less. On the water front, there's a lot of uncertainty, and the water requirements depend on the climate. The values quoted in the literature range from about 2 to 12 kilograms of water per kilogram of CO2 captured. And these actually, again, favor or compare very favorably with BACCS and afforestation water requirements. And we quickly estimated that using the higher end of the water requirements, to have 8 gigatons of DACCS removal would require about 1.26% of the global agricultural water use, which doesn't seem to be high. And therefore, overall water demand is not expected to be a large restriction in most regions, except for areas which are very dry and hot. I mentioned that it was possible to reduce these costs even further in the future. So here we considered several cases and we tried to reach the lowest costs we could reach. Starting with liquids here, case 1 is just representing the base case of a hybrid liquid plant at $194. Case 2 is looking at the same plant situated in a cluster, so it has less transport and storage costs. And case 3 is looking at the same plant with lower cost solar availability. Case 4 is using a next generation electric plant, which is a technology that carbon engineering is currently working on, and combining it with low cost solar energy. So costs around $130 may be achievable in that case. And case 5 is the most ambitious case, where the plant has access to low cost, very low cost solar, situated in a cluster, has a lower discount rate of 3%, and is a next generation electric plant, and the costs can be around than $100 finally. So in certain circumstances, these low costs may be achievable, but it may not be appropriate to assume that would be the case for the majority of locations. And now the same for solid DACCS, again starting with the base case of a hybrid plant at $230, and case 2 is looking at a low adsorbent cost if the adsorbent learnings are higher than the base load. Case 3 is looking at the cheapest energy option, low-cost solar, free waste heat situated in a cluster. And comparing those two, you can really see the importance of adsorbent prices. Case 4 is looking at an electric-only plant with access to low-cost solar, and that by itself is not reducing costs too much. And finally, the very ambitious case of combining all of these things together can this time achieve the cheapest prices we investigated, which was $78 per ton. So it's really, really important to combine adsorbent cost reduction with access to cheap electricity. And in this final section, I want to talk briefly about some of the policies and the recommendations, reminding you that the study was conducted the first half of last year, and since then some other policies have emerged to a degree, but still robust and largely applicable financial incentives providing revenue certainty is absent. So some of the notable incentives for DACCS include the 45Q tax credits, which is currently awarding only $50, but the proposal is increasing this substantially for DACCS, and California's low carbon fuel standards, which is allowing DAC plants anywhere in the world to sell into this market, as well as some procurement policies such as the Buy Clean California Act. And since then, for example, reverse auctions have emerged in Sweden for BECCS credits, and an independent group is working on developing a feed-in tariff called Luxembourg's feed-in tariff for procuring negative emissions in Luxembourg. So there is some emerging thinking around these financial policies. Now here we list various options available for governments to incentivize DACCS, and on the left are options which incentivize projects proportionally to their operations or on a per ton of CO2 removed basis. And on the right are some options for targeting high capex or investment levels. And the idea would be that governments should, depending on their preferences and experiences, choose which one of these options would be suitable for them. So some of the policy mechanisms for operational incentives including DACCS in an ETS system, or creating a new regulated negative emissions market, perhaps introducing an obligation scheme for fossil fuel suppliers or emitters, developing clean energy standards like the California low carbon fuel standards, tradable tax credits such as the 45Q tax credits, direct procurement, or carbon contracts for differences, which were used very successfully in the power sector in the UK. CapEx related support then includes tax credits on capital investments, loan guarantees, low interest loans, accelerated depreciation, direct capital support through grants, affordable finance, and the like. And finally, the CO2 transport and storage aspects shouldn't be forgotten, as it is essential for DACCS value chains. And depending on the government's preferences in different regions, this can be in the form of a state-owned finance model or a regulated asset-based model. In addition to the financial policies to enable DACCS, there would be a lot of other enabling and supportive policies or actions to create the ideal space for DACCS rollout. And some of these include more prominent or direct support actions. For example, creating a robust negative emissions technologies certification framework, developing standards for measurement, monitoring, and verification, establishing consistent regulatory frameworks, considering in the US, for example, harmonizing regulations between states, or in Europe between countries, streamlining and accelerating permitting for DACCS, including permitting for renewable energy as well, and perhaps separate targets for CO2 mitigation and removal, which can help with addressing the mitigation deterrence risk. Some less direct support includes having strong and effective governance structures, taking into account social considerations for policy making and decision making, having international cooperation and leadership, especially around these standards, including DACCS and national decarbonization roadmaps to signal the importance of the technology, and several other items listed here. Finally, to wrap up the main messages, I think the key takeaways are that currently DACCS is an expensive technology, and future costs may fail to meet the $100 per ton industry targets. Energy prices, demand, capex, adsorbent performance, and plant lifetimes are the most important factors for cost reduction. And in certain circumstances, significantly lower DACCS costs may be achieved, according to our calculations. And lastly, substantial financial incentives and enabling policies are needed to establish a bankable business case for DACCS and remove barriers to commercial scale deployment. Now, thank you very much for listening to me. I'd be very happy to take questions now. And also, if you have any follow-up questions or comments or inquiries, please feel to get in touch with us. And I also encourage everybody to check out the full report for more of the details in the sections that I wasn't able to touch upon.
Yes, thank you very much for the good presentation, Yuri. And we have collected a couple of questions. First of all, I want to say it's one question that popped up and is not related to technical content. The recording and the slides of this webinar will be made available after the webinar for those of you who were wondering. And so let's start with the first question. It's about the costing models. And the question is, how and if did you take replacement costs into account for both the liquid and the solid solvent in terms of degradation?
Yes, so sorry, Jasmin, I have a little bit of feedback from your end. So we,
or
if you can mute yourself, I'm getting a little bit of feedback right now. So we included adsorbent and absorbent prices as non-fuel OPEX. So we considered them as a cost as a dollars cost per ton of CO2 removed. So we didn't explicitly calculate how much would be needed in a column and how frequently it would be replaced. We rather considered it as an almost ongoing consumable. And that data came from carbon engineering for the liquids and for the solids, based on our best understanding, our discussions with some of the technology developers, because it is highly sensitive information and there are a lot of trade-offs between performance and the cost of those adsorbents. So it's one area where there's a bit of vagueness and there's a lot of room for future improvements.
Yes, thank you. Then one question, whether will be any future evaluation of the carbon collect technology that uses natural air movement. I mean, it was not in the scope of this study, but do you have a view or opinion on that?
So we haven't modeled that. We only focused on liquid and solid DACCS. But what I can say about these emerging technologies is that when this study was formed and performed, the general idea was liquids and DACCS as the two prominent leading technologies. And since then, the various other DACCS options emerged. For example, here in the UK, the government had the 100 million pound GGR innovation competition, and I think the phase 2 for a demonstration program will be announced soon. But there are a lot of projects which got funding, and more options and technologies are entering into discourse in this space. So probably, yeah, we will hear more about these innovative options in the future.
Okay, very interesting. One question is, what is the DACC plant capacity associated to the seen reduction in LCOD, and whether you can further elaborate on the timeline and or investments needed for that?
So is this about how much investment will be needed for, or the total capex requirements? I guess.
Yes, I would assume so. Yeah.
Okay.
Yeah, we have seen the reduction over a certain either timeline or, as the study actually did, ramping up in capacity, and yeah.
Yeah, so how we approached to cost reduction was not a specific learning rates multiplied by the capacity requirements angle. We again, in discussion with technology developers and the publicly available data, estimated where the costs can go in the future. But then we looked at, because also these learning rates are highly debated, and different technologies can have different learning rates. For example, liquid technologies use slightly more established processes, which may have less lower learning rates. But when we went back and look at our costs, we figured that this approximately corresponded to 5 to 7 doublings of an initial capacity of, say, around 1 megaton or 2 megatons of removal. So I guess that can give you an idea if you just take 2 to the power 5 or 7, that gives an idea. But we didn't calculate how much it would cost in total to achieve there.
Okay, the next question was, it might have been in the presentation, I'm not sure, what is the low-grade waste heat requirement for the solid adsorbent process in gigajoules per tons of CO2 captured?
I will have to go back and look at the appendix for that. So I don't have that number. It
probably should be in the report as well, right? Yeah.
Definitely. All of our data are in the report. And also, I didn't really talk about the IEM modeling elements in this webinar, but we have a section collating the information that we used and presenting it in a nice format for modelers. So definitely there's much more information in the model, and I can't remember the number off the top of my head.
There was a question related to the flexible operation. And the question is, would the solid storm process be able to operate flexibly with solar availability, which means full-scale solar input, or is it unrealistic?
Yeah, so from a technical point of view, technology developers are positive that they can operate flexibly if they have to, but they're not really considering it as a viable model. I guess for solids it may be easier. For liquids, they need to maintain a very high temperature, so they can't really shut down their whole plant. But what they can do is they can operate the capture component flexibly, and then save some of their calcium carbonate pellets and operate the downstream CO2 release process continuously. So from a technical point of view, it seems like they can do it. But our estimations show that from a financial perspective, it may not make too much sense right now.
Okay, thank you. Then one question more on the policy side. Do you have an opinion which would be the more easily applicable policies to incentivize DACC?
Yeah, this is a very difficult question. It depends on the specific country, I suppose. What I can say is Element Energy is working on another project with BASE, which is the UK Department of Energy. And we're looking at different policies to incentivize GGRs and specifically DACCS in the UK. And I guess the short list of policies we ended up with are carbon CFDs or direct payment schemes and or obligation schemes. They're slightly different, but of course this reflects the UK's experience as well. Good experience with carbon CFDs. If we were talking about the US, for example, then tax credits may come into play. And also, the long-term goal is to have a market-based mechanism and maybe integrate with the UK ETS. So in Europe, integration with the EU ETS may be a nice emerging option too. And if additional funding is needed, then it feels like the CapEx support mechanisms are all equally preferable by the tech developers. But maybe a guarantee scheme may be more feasible for the government.
Then, how do you see the carbon market develop and use carbon credits for the CO2 captured and stored, removed by DACCS?
It's a very difficult question indeed. This is something we considered in the BASE study. There's a lot of uncertainty around voluntary markets and how they can develop. But the current problem is there are some voluntary transactions going on right now, but they're at very small volumes. So at larger volumes, probably companies won't be able to, or they won't be willing to pay too much more over the minimum credit prices they can purchase. So DACCS would struggle with that. So there needs to be bridging policies probably to mitigate that, or some sort of an obligation scheme to force people to buy DACCS credits. But it's a difficult question, and with the Article 6 of the Paris Agreement, there are still a lot of uncertainties around whether projects will be able to sell to other countries and what would the implications will be, and there probably countries will have to make a choice, because obviously allowing selling into other countries can crowd in public finance, but then why would the government? There are political implications. So there are too many uncertainties right now.
Then one question about that currently publicly shared cost for 1 ton based on the plants that are currently operating is about $1,000 per ton CO2. And so the data we have seen in this report now shows quite some lower estimates for the cost. And what are the main drivers to achieve this very low cost? And do they have to be seen as pretty optimistic? And I think you have already commented on that when you went through the cases a bit, but maybe it's another chance to elaborate on that and clarify it.
Yeah, so the Climeworks credits are, I think, sold for around that much right now. But the biggest difference is, I guess, so we're modeling larger plants benefiting from learning curves, and Climeworks plant is pretty much an experimental plant. They're still figuring out a lot of parameters, learning by doing that. That's why they're not directly comparable. And I guess for solids, our FOAC costs were around higher than $600 anyway. So I don't think we were so far off from that. And also for liquids, on the other hand, Carbon Engineering has done a FEED study or they're undertaking a FEED study. They've done a pre-FEED study for their proposed 1 megaton plant in the US. So they have much more detailed cost estimations, and 1 megaton plant obviously benefits greatly from economies of scale. So that's one of the reasons why they can claim much lower prices.
Okay, thank you, Yuri. And then for the energy requirement for liquid and solid DACCS, did you use values from literature, or did you use your own modeling to do the costing then?
For solids, we used the literature. For liquids, we used data provided by Carbon Engineering. So yeah, we tried to combine both sources. We didn't do engineering work in this project. We just did a high-level techno-economic work. Currently there's a lot of uncertainty because technology developers can be thought of as biased. We realize that, but also academics are usually divorced from what's happening in the startup world or actually by these companies. So we try to bridge that gap as much as possible.
Then one question about fugitive emissions of the absorbent per ton of CO2 captured from the DACCS plant, and also what will be the impact of any fugitive emissions from a large-scale DACCS system on vegetation, soil, environment. Do you have any information for that, and or do you know about any studies that were done in this area?
So we didn't look at direct environmental impact beyond the land and water requirements. There are a couple of LCA studies, I think, published in partnership with both the Carbon Engineering and Climeworks. So it's possible to go back and see what their LCA emissions are, and I think we use them in the study. So for the adsorbents, the embedded carbon we assumed came from the published LCA studies from in partnership with Climeworks in collaboration with other academics. I think we use an average value for a representative adsorbent because we actually don't know the actual adsorbent they're planning to use, and I think that's changing as we go along. So yes and no, but I may be able to yeah. I don't have too many studies that I can think off the top of my head, but maybe can answer through email better.
Okay, then we briefly mentioned, or you briefly mentioned, about the assessment that was done specifically for recommendations for integrated assessment modeling. Can you share any highlights? I mean, if you don't have it on top of your head, we could just refer to the report. It's all in the report. Time today was just a bit short to get through everything.
Yes. Also, that section was done with collaboration with Dr. Adam Hawks from Imperial College. Yeah, I definitely recommend you checking the report. I guess, yeah, one of the interesting findings was that currently DACCS was represented as a single technology, and it didn't really consider liquids versus solids, or hybrid versus electric only operations, and I think used also grid carbon intensities as well. So those were some of the areas where we recommended improvements. And also, yeah, tabulated our data in a nicely way to be used by the modeling community. But yeah, I won't be able to go into too much depth on that, unfortunately.
Okay, thanks, Yuri. Then one question is, as we just were touching on the environmental issues and impacts, how reliable is a DACCS application in a relatively air polluted environment, for example, a megacity, and would any particulate matter impact the performance of the process, any impurities in the air?
That's an interesting question, and we didn't consider that, to be honest. So yeah, I won't be able to comment too much about impurities in the air, and I don't recall technology developers really talking about it. But I recognize that some DAC companies are turning into air cleaning companies in the startup world, so that may be an indication. And I heard DAC being proposed as an add-on to ventilation systems in large buildings. So there may be something interesting around that, but yeah, no, I don't know too much about it.
And then maybe one last questions. I think we have almost tackled all of them. As demand increases, will DAC costs ever be able to match nature-based offset costs?
Interesting. It feels like nature-based is likely to be always cheaper, depending on how the accounting will go. Now, there's a lot of discussion around how to account for. So, is a ton removed by nature-based solutions the same as a ton removed by DAC? How long is the carbon removed for? Do you have to renew your credit every 10 years or 20 years, or do you need to buy multiple credits to offset 1 ton of CO2? Because you know that that removal is not permanent. So if you introduce all these things, then they can be comparable. They can be cost comparable for sure at the NOACS stage. But otherwise, I struggle to see how nature-based solutions, by and large, will be much more expensive than DAC. Depends on the country, of course. If you're trying to do them in a country with limited resources, then that may be correct. But probably that's not DACS getting too much cheaper. That's nature-based solutions getting more expensive.
Okay, thank you very much, Yuri, for answering all those questions. And I think with this, we are at the end of today's webinar. Thank you, Yuri, for presenting, and also thank you everyone for attending and putting forward your questions. And again, as we said, recording and slides will be available later. So thank you for being with us today. Goodbye.